So I'm back to the official class stuff. The hacking workshops are not going to happen again until December. Lan is sick, so it won't happen this Saturday, coming up in 3 days, and after that it's Thanksgiving vacation. So the next thing that will happen will be this invitational on December 6th. I highly encourage every student interested in cybersecurity to come to this. You do not need to compete. You can watch and learn. You can join it. You do not need to sign up or meet any requirements by taking a certain number of classes or anything. That's what the invitationals are. The invitationals are just practice events, not official competitions. And everybody's welcome to come, and you'll get to see what it's like. These things simulate a real corporate environment. The students are controlling a network of about 10 machines with servers, and they're trying to keep business activities running on those servers and getting management requests constantly to do things and getting hacked, and trying to defend themselves from being hacked while they're trying to keep it going. So it's very much like what happens in a business, and everybody's welcome to come watch and see how it works. All right, but that's the next thing that will happen on Saturday. Other than that, there's just my ordinary Saturday class. None of these workshops, I'll add to this later. The next two are not going to happen because of Lan being sick and because of Thanksgiving. All right, right. So we're coming to the end of this course, the end of the whole semester. It all happens real fast at the end, so here we are. Today I'm doing the second part of Chapter 2 and another demo, and then we're going to do 2 lectures on Chapter 3, and that's it. So you should check your scores in Canvas. They should all be updated, and everybody should know how they're doing, and you still have a couple of weeks to catch up if necessary. So let's take a look at iOS apps, which, like I say, unfortunately, we only talk about them in this class. There are no hands-on projects because unless I have a room full of Apple hardware, I can't really set up hands-on iOS apps that students can do because you have to have exactly the same version of everything. So we're down to this, the data protection, the keychain, and how binaries work. So Citigroup made a mistake in their iPhone app, which is fairly common. They saved a local file that had all kinds of personal data in it. This happened to a lot of people. This even happened to Nessus, the security scanner. The first version of Nessus that ran, I think, on Android just saved your password on the SIM card in an unencrypted file. A lot of people, when they made phone apps, they just didn't know what they were doing, and they made ridiculous errors. And as you've seen in this course, by the way, the restricted projects are no longer restricted. These guys have had more than a month to ignore me. So I took the restricted projects, which are the recently discovered vulnerabilities, and I just added them to the main page here. If I can find, yeah, new projects, here they are. It's all, these guys all had more than a month to patch it, and only one app patched it, so now they're not secret anymore. So anyway, but that's the point. Nothing seems to have improved in the last several years. I've been doing this maybe 10 years, these vulnerability scans of Android apps, and they continue to be complete crap. Although plain text login is very hard to find now because they updated the operating system, so it gets more and more difficult to write an app that will do that. So that's beginning to go away. But these other flaws don't seem to be going away anytime soon. So iOS has a lot of encryption. It's I always tell people iPhone is your safest computing platform. Of anything you can buy, you're most likely to not get hacked on an iPhone. Although there are these very dangerous things like Predator and Pegasus that will do it. And there's all the commercial spyware, which is not really a security vulnerability. If somebody can get your phone and install an app, which means they're able to get it in an unlocked state, then of course they can put a spy app on it, but this is not a normal attack. This would be somebody in your family. They can get your phone. And there's really nothing they can do about that. But anyway, so you have a encryption key, several levels of encryption we'll talk about, and you have a secure enclave, which is the equivalent of a trusted platform module, a special chip just to handle encryption and keys, so you can't steal the keys with any app or malware. So the passcode key is derived from your passcode. You type in a 4, or these days more likely a 6-digit passcode, and in fact on mine I switched it to alphabetical, so it's a real password, which is of course even more secure. And then you just derive a key from that, and this is quite easy to do, and we'll be doing it in the cryptography class next semester. All you do is this thing called password-based key derivation function is extremely simple. You just run it through a hash function like SHA-1, and you do it like 5,000 times. And then you add a random salt to it first usually, and then you just have a way to create a encryption key from a passcode, which is deterministic. Every time you enter the encryption, the passcode, you can get the key, but then you have a key of the appropriate length to do encryption, which is almost always done with AES. That's the whole point of AES. AES is the recommended encryption scheme for general purpose use. You encrypt stuff with AES, you have very high degree of security, but it's a private key encryption. In this case, you don't have a private key you need to store on the phone. The user has to type it in. They type in the passcode, that's turned into a key, you encrypt the stuff with the key, and the key is not stored anywhere on the phone. You have to put in the passcode. That's why this is good. It's not like some artificial barrier where you have to put in the passcode to get past a page. The passcode encrypts the data. It is simply impossible to recover the data without the passcode. This is a very smart solution. It doesn't require on any operating system security or technology of any kind. It's just the fact that the key is not anywhere on the phone. It comes from your passcode. All right, so that's the idea. And so now you have levels of protection. There's things protected by the passcode key, and there's things protected by the device key, which is some piece of hardware in the device that gives it a key. And then you can have things protected by individual file keys. So there's many layers of encryption in the iPhone system. They're really not messing around. And this is quite reasonable because AES was designed to be really fast. And it is really fast. So you can have something encrypted with 3 layers of encryption and it won't even drain your battery or slow it down very much, because not only is the AES algorithm really fast, but modern processors have built-in AES machine language instructions. So they do AES really fast, really easily, so there's nothing to stop you from doing lots of encryption. It's quite easy. So you can have things with no protection, have things with complete encryption, encrypted when the device is locked, and then complete unless open. So if the file is in use, it's unencrypted when the device is locked. And so this is what you might do for things like your instant messages will pop up on the screen even while the phone is locked. So there are certain things that run even while it's locked, and you can adjust that, but often you want that. So your messages pop up, and of course the risk is if somebody steals your phone, they could see that, even though they don't have the PIN, so you make that decision. But most of us, that's okay. In fact, it's probably not a very good idea because SMS is usually your second factor for authentication. That means someone could steal your phone and read the second factor even though they don't have your PIN. So if you want higher security, you'd probably want to turn off showing things while it's locked, which you can do in the settings. All right, and so then complete encryption until first user authentication. This is encrypted only from boot up to first unlock. And therefore, the safest way to protect your phone is to turn it off. If you steal a phone while it is turned off, you're pretty much going to be unable to extract the data from that phone. If it's just locked out, but showing the lock-in screen, then there are ways to get past that sometimes. That's the issue. And the police have tools to try to break into the PIN. One of them is the gray key. What it'll do, now if you put in the wrong PIN 10 times, it'll wipe the phone. So there's a gray key device you plug in, and it will try 9 pins and then reboot the phone. And then another 9 pins, reboot the phone. And you leave it go like overnight, it'll break in. It'll try them all. And there are other devices, better ones from Celebrite that cost more, that will find a flaw and really break in. So there are ways in, but if you have like a 6-digit PIN, then no one's going to get in unless they pay for the expensive Celebrite stuff. And that stuff costs $1 million. Average police departments don't have it. The FBI bought it. And, various people who really want it can get in, but that's all you can ever do. Nothing's ever secure, complete security. All you can do is raise a barrier like a fence to a certain height, and there's always attackers that can get through, but you stop the ones that are weak enough not to get through. You just have to decide through a threat model, who's attacking me? Is it just criminals that want to steal credit card numbers? Because they won't try very hard. They'll just go steal somebody else's credit card numbers. If it's the U.S. military or something after me, then you're screwed. There's nothing you can buy that will stop them, All right. So the keychain is where you can store secrets, and so you can have things that are accessible always in the keychain, things that are only accessible when the device is unlocked, things that are only accessible after the first unlock from a boot, so it's powered off, you can't get into them. And these are just various levels of security. And then you have things that can only be accessed on this device and not another device, only when this device is unlocked, and so on. Various levels. That's why I say all of that complicated diagram with all these different types of encryption, you can adjust the security level of all the various things stored on the device to these levels, and the app designers do that. They decide what security level is appropriate for the various parts of their app. So iOS also has You cannot get to these things when no passcode is set on the device. Some people, I don't know if anybody still did this, when phones were new, people would just have no passcode. You open the phone and use it. I think everybody learned to knock that off. I mean, that's pretty outrageous. Everybody can get your emails, see your photos and everything. I think most people have a passcode on, but if you don't have a passcode, then of course you shouldn't let people get at anything private, obviously. And I've seen this in the Android emulators. Like if you want to download a certificate to authorize burp, you can't do it until you put on a passcode. Anything related to security, it says, well, if you don't have a passcode, then this is ridiculous. There's no point doing anything in the security until you at least have a passcode. All right, so the keychain is a SQLite database, and you can use Keychain Dumper to dump it if you have a jailbroken iOS device, but the stuff is encrypted unless you have the keys to decrypt it. All right, Touch ID is fingerprint sensing, and so if it's not enabled, then you have this complete protection class here. I'm not quite sure what the deal is here. But if it is enabled, then your keys are not discarded but held in memory. So this is the way the Touch ID works, is it recognizes your fingerprint and then releases the keys, and the keys are held in memory. So you could argue that this makes your phone somewhat less secure. It has to have the key. This is true, I think, of Bitcoin. This is why the cold boot attack works. Not Bitcoin, it's true of Microsoft encryption. The original key is in the trusted platform module, but if you, once you log into a Windows machine and it decrypts the hard drive, it stores the key in memory so it can continue to decrypt it. And if you go to standby mode, the key is still in RAM. So one of the attacks is you take apart the computer, you freeze the memory, then you take the memory out and put it in a Linux machine and you read the memory, because if you freeze the RAM, it will remember the data without power for about 15 minutes. So you can pull out the memory, put it in another box, read the memory, and the key is actually in RAM while the device is in standby mode. And that's the same thing here. The fact that the key is stored somewhere for a while means that perhaps you could do something like that. You could take apart your phone and steal the RAM out of it. That's, again, a pretty exotic attack. I mean, but anyway, all right. So Chaos Computer Club broke the Touch ID, and they did it by taking a fingerprint of the user, a photograph. You just run your fingerprint from like a glass and create a fake finger. You do this for like silly putty and stuff. This is the problem with biometrics. They can take an accurate model of your face. Now, I've been told, I haven't tested, I've been told that the face scan for facial recognition on the iPhone is not just a photograph, but it actually sends out like an infrared laser and scans the three-dimensional shape of your face. However, I've also been told by people that like a mother takes it home and her daughter can open it because their faces are similar enough. So I don't know how perfect it is. And this is the problem with all biometrics. They tend to be foolable. I know, what's the one, there's now the age gating. A bunch of social networks in Europe, and kids have found that just a photograph of like a character from a video game will do it. You feed them that picture of like a character from a video game, and that'll prove you're an adult, you can get in. And so, you know, that's the problem with biometrics, and especially fingerprints. Fingerprints are pretty stupid because you're just leaving them everywhere you go. Anybody can easily get your fingerprint. And I mean, there was a guy that pushed fingerprints as the answer to everything. So a rival security company published an ad in a security magazine of his thumbprint. Said, okay, what now, wise guy? And that's the problem. Also, if somebody does steal it, you can't change it. So, you know, that's a limitation of this, but you can't beat the convenience. Now, I'm spared from this because Apple devices do not recognize my fingerprint. I train them, and it doesn't work. I've tried it over and over. I don't seem to be a regulation human. Everybody else uses it. The facial recognition works. The fingerprint never works because a little tiny pad, I think, and my fingers are too big. I never get exactly the right spot of it on there. They say they're taking care of that. You have to press it like 20 times, and it draws a complete picture of your fingerprint. It looks like it's going to work, and then it totally doesn't work. Not for me, anyway. So, but most people it seems to work for. Anyway, they just managed to make a fake fingerprint, which is pretty easy. And so the binaries that you have are in this format called Mach-O, as opposed to Linux executables that are ELF and Windows executables that are PE files. This is the Apple format, Mach-O. So it has a header, and then it has the layout of the symbol table and the libraries and such, and then the data. They all amount to approximately the same thing. So you have the commands to load it, and then you have various data stored down here. So they often are fat binaries because that means they support multiple hardware editions. So it can run on ARM32, ARM64, and Intel or something like that, different versions. That's called a fat binary with a version for multiple operating systems to support different architectures. And here's the architectures. They're all ARM64, and I think these are 32-bit ARMs. These are the 3 versions of processor used in iPhones. So if you really want everybody to use your app, you'd put all 3 of the executables in one file, and that would now be a fat binary. So you can use OTool to see it. And so here you can use OTool as a command line tool to show you what architecture it supports. And here it'll show you that this thing supports ARM7 and ARM64, which is in the CPU subtype 9 and subtype 1, I think. Actually, I think this is the this big number. It is like 1, 9, and 16 million. It's kind of ridiculous numbers. We'll see a chart as you go ahead. Yeah, here they are. It's CPU type, 12 and 16 million. I don't know why they made up these numbers, but those are the ways you can tell. Anyway, those are the various ARM architectures used by iPhones. And so you can take the tool called LiPo and remove 1 from the fat binary and make it a skinny binary if you want to, so you get down to just 1 version, which is something you might do to simplify your reverse engineering. And by the way, the same thing's been true of our Android apps. Might as well mention that. It happened, especially the newer apps. This happened with quite a few of them. And actually, it happened with Keeper. If you go, not that one, but this one here is the same way. These are what you would call fat binaries. When you look at the app is not just one file, it's a whole series of files. You have the base stuff, and then you have the Intel stuff, and then this and that broken into pieces. I think this is for Intel, and there's a separate one for ARM, and I'm not sure what these various things are. This app is several different pieces that have to be installed all together to correctly install it, and that's what fat iPhone apps are like. So then there's the security-related features, which are the same thing you hear in all my classes about security. These are the ways you protect any kind of software on any operating system. Address-based layout randomization is Microsoft's term for this, where every time you launch a program, it randomly moves it in memory to a random location, just to make it hard for the attacker to find it and attack it. And that stops a whole generation of buffer overflow attacks. You need to have position-independent executables. They need to be compiled with the features to allow this, which means every time your app refers to an exact memory address, it keeps a table of those so it can rewrite them all every time you move it in memory. If you don't have that, then it cannot be relocated. It can only be loaded at one memory location, which was the default before about 2003. Nobody thought about this. Your apps didn't move in memory. They just load in one location. So, but all the Apple-built apps have this since a long time, which is more than you can say about Microsoft. Microsoft has a bunch of stuff that doesn't relocate. Because every time Microsoft has a new security feature, they only implement about 80% of it. It takes a while to get used to this. It sounds really great, and then you find you can still get away with murder every time, because Microsoft is very, very dedicated to supporting old stuff. They are held back by supporting decades of legacy stuff, which is important for business, because you have some all-important app at your company, like your cash register app that was written for Windows 3.1, and you're still using it, even though you want to run Windows 7 or Windows 10 or Windows 11, and Microsoft will support that. But that means they have tons of really old stuff in there that is like, drags them down from viewpoint of security, but it meets the needs of business, and the purpose of Microsoft is to serve business. Apple serves only home users. That's all they care about. And they're perfectly happy to tell home users anything more than one version old, forget it. We don't support it. You're supposed to buy a new machine. And most Apple people will do it. They'll cheerfully keep buying a new machine. So they have no interest in supporting business. So they don't even have domain controllers. They don't even have some way to scan your network and find out what version people are running and make sure they're all at the same version. Stuff you really want to do in an enterprise, they're not there for you. They don't care about that at all. They only care about home users. Anyway, so stack smashing protection is another one. When you enter a subroutine, if it has a string variable, so it can take some kind of words or text, then if you can put in too much text, it exceeds the reserved memory for that, and then you can write to memory you're not supposed to be able to write to. And if you can write far enough, you make it all the way out of the current stack frame to the return pointer, which is used to return from a subroutine, and then you can redirect execution from the place the developer wanted to go to a place of your choice and take over the machine. And this is how the classic buffer overflows work. And we'll do them next semester in 127 in great detail. The canary value is added to the end of each stack frame before the return pointer, a random number that it knows, but the hacker doesn't know. And so if that number changes, the program stops. It does not attempt to return. It just crashes instead of letting you take it over. This is a powerful defense against buffer overflow attacks. And so it's included. However, I notice Apple does the same thing that Microsoft Visual Studio does. It does not apply this all the time. They're afraid, I guess, of the performance penalty, which must be larger than I would imagine it is. They only apply it when you have string variables that look long enough that might be overflowed. So I'm surprised. I would have thought just put it on all the time, but my main focus is security, and of course their main focus, most people, is to please the end customer and make it fast and pleasant and availability. So this is the thing we spend all of our lives in security doing. The early security people are like, no, you have to do this, you have to do that. And they say, well, nothing is ever absolute. You have to take some risks to get the business done. So the real point of security people, like lawyers, is not to stop you from doing anything risky, but to help you make smarter decisions and take calculated risks. If you tried to worry about every possible thing that could go wrong in security or the law, you couldn't do anything. Like this college is about as benevolent, a harmless contribution to the society as you can get. It's free classes, open buildings, people can just wander in, and they get sued all the time. You can be as good as you can be, and you'll get sued. They got sued because the sidewalks were cracked and they weren't shallow enough for the wheelchairs and stuff like that. Whatever you do, there's a legal risk, and there's a security risk, and our job is to help people do what you need to do and lower the risk as much as possible. Anyway, so they have this smash bashing protection. They also have this thing called automatic reference counting, which is another one of the insane things. By the way, all three of these are caused by C and its derivatives. If you just wrote your code in Rust, none of this garbage would happen to you. And this is another one. If you want to use memory temporarily and then free it to use it again later, you use malloc. You allocate some memory, you store some data in it, then you use free to stop using the data, and then you can reallocate it later. The problem is in C, there are three things you must do. You must allocate it exactly once. When you're done with it, you must free it exactly once and set the pointer to null. That's what you must do. And this is on the developer to remember to do that. If you fail to do that, then you have flaws like a dangling pointer, where you free it, but you forgot to set it to null. So there's now a variable that points to memory that you can use to read and write to memory that is now being used for a different purpose. That's one form of memory corruption. A double free will perform the free activity twice, and that can lead to a write that you can control. And if you don't free it at all, then you have a memory leak, where it just keeps using up memory until it crashes, which was true in Windows 95. And these things tend to happen. In Rust, none of this ever happens because it's handled automatically. As soon as you allocate memory on the heap, it just looks at what code you're in, and as soon as you exit that segment of code, it automatically frees it. You can't free it twice. You can't free it 0 times. It's not up to the developer to remember this. And this might sound simple, but of course it's not, because real projects have many subroutines, many connected things, and many developers. So even if you do it right, before long somebody has added another function call in the middle of it, and then they've added some other code written by somebody else where the free is in a different routine, so you get calling it twice, or maybe not at all. Pretty soon you lose control. The problem with C is just too hard to write good code. There are too many ways to go wrong. Sooner or later it'll happen to you, that you have a string and you forget to check how long is the data coming in. You just have to remember to do that yourself every time. And sooner or later somebody on your team is going to forget. Or you'll integrate some old library to add a feature that was written before anybody knew about this, which would be before 2002. When Microsoft built Windows XP, their entire team had never heard of what a buffer overflow was. They had no idea about any of this. They learned about it. So around 2004, Bill Gates stopped all development on Vista, and he made the whole developer team read a book called Writing Secure Code and rewrite Windows XP in its entirety and give it away for free as Windows XP Service Pack 2, basically writing off 1 or 2 years of Microsoft profits. It was a highly controversial business move, but he said this security situation is so bad, we have to fix this. People are getting really fed up with their machines being totally hacked and alligators dancing in the corners and everybody porn popping up on the screen. He said, but you just have to give them a free security patch, which is what he did. And so any code from before that time, nobody knew this, and people just wrote code that was just full of these flaws. And everybody, nobody cared until the hacking got out of hand, which was, from like about 95 to 2005, everybody was getting hacked all the time. It was just ridiculous in chat rooms and everywhere because it was so easy. All you had to learn was a few basic attacks and you could take over stuff everywhere. And Microsoft led the way, getting more and more secure to where they really are a lot better. But it took a long time. Anyway, so automatic reference counting tries to make sure that things are getting freed the correct number of times, which is once each. All right. So your App Store binary apps in the App Store are encrypted for digital rights management, just like they encrypt music files to make sure you don't get an unauthorized copy. It decrypts when you load it through the App Store. That's why you can't get a copy of the app outside the App Store. And so then you have to decrypt it. You can run the app and you can attach with a debugger and find the base address, retrieve the memory segment, write the decrypted segment with DD. There's a process. If you have the app installed on an iPhone and it's a jailbroken iPhone, you can then run these tools to extract an app from the phone. It is a lot more difficult than it is with Android. So there are tools to try to automate it, but of course they all work only on one particular version of everything because Apple keeps changing all their security in big ways too. Like about 10 years ago, they started compressing RAM on the Mac, which, by the way, is pretty brilliant. If you have only like 4 gigs of RAM and you start opening apps, pretty well you've used up all 4 gigs, and then it starts paging to the hard drive and getting much slower. So app zips it in memory, which is pretty brilliant because that's a fast operation and you fit more stuff in RAM. The problem is all the memory extracting tools don't work anymore. You have to update them. Anyway, so they do a lot of this. And so you can dump the classes, which gives you the names of routines and variables, not all the code. So you can do that. I did it to the Starbucks app here. This is what you get is some horrible mess like this from, I said somebody else did. This is what you get from this dump. You just get the name of all the routines and where they are, which is give you some idea what the code is doing, but not complete code. You can, however, disassemble it with disassemblers designed for the purpose, and the free one is Hopper. And years ago, I used to have projects where students would do this. You can take apart and decompile this stuff down to decompiled sort of C++ looking code in Hopper, and then read in here and try to find things. But it was very difficult. And like I say, if I wanted to do a class in this, we would have to have a lab with a bunch of iPhones and a bunch of Macs, all exactly the same, and everything would have to be done in that lab. That's the only way to get here. Other devices different from this device ID or other Apple devices? Yes, that's right. That back there, I didn't see your question. Yeah, when it says other devices, it means other Apple devices. In the whole Apple ecosystem, you never think about going off Apple stuff. It's a closed system. All right, so let's try a Kahoot. Oh, good. And I think there's 2B we're at. Yeah, 2B is here. All right. There was, when I went a couple of years ago to DEF CON, there was the Telefreaks party, and to get in, you had to go to a website, and you had to answer about 20 questions about a movie called Repo Man, which I'd never seen, and I tried answering it all using AI. But there were like 5 questions towards the end that you actually would have had to watch the movie to solve. But yeah, I got pretty far without knowing anything about the movie, just asking like ChatGPT what the answers were. Anyway. All right, what's up? What ID? Face ID. It's a good question. I don't know exactly how Face ID works. It's a very good question. I don't know the answer. I know it does not store a literal picture of your face. It somehow calculates some kind of number from your face and stores that. And they'd say this means people can't steal your face from it. But, you know, I wonder what it is. I know fingerprint analysis, they find like certain points where there's a cross. It would be good to know more about it. What exactly did it measure about your face? And therefore, how good would I have to make a model to fool it? And could I somehow take that and rebuild the structure of your face and thus compromise your privacy? It'd be good to know that. Yeah. It's a good question. I don't know exactly how it works. It would be nice to know how it works and how secure it really is. Like I say, I have heard anecdotal reports of people that say another face in their family will fool it. So I guess it's not that great. I think it's better. Now, when Lenovo first came out with Face ID, it wouldn't work at all for black people. And I think iPhone did better than that. I haven't heard that complaint. Because that, I think, was working off a photograph of your face, and if you didn't have enough contrast, it wouldn't see anything. The Apple, I think, does something better than that anyway. But I wonder how good it is and how easy it is to fool. Let's give it a shot. All right, so which key is controlled by Touch ID? Okay. I think I know. Well, I'm wrong. Oh, okay. I thought it was the passcode key, but it isn't. It's the wrapping key, right? It's a key around another key. That's what it uses to decrypt it. All right. Anyway. I say this stuff is pretty impenetrable. Although my one student spent like months going through it and figuring it all out and found a new jailbreak for the iPhone. So it is possible to figure this stuff out, but it's pretty dense. And he tried to explain it to me, and I really never got it very much. He really untangled it all and found a way to hack through all these layers of encryption. But I only know in general terms how it worked. All right, so what's the file format for iOS apps? It's Mako. By the way, I don't know why it's not ELF. iPhones are running Unix. They're running BSD Unix, which they advertise as the most advanced operating system in the world, and I think that's true. It was the original Unix from Berkeley. It was the one that started it all. It's the oldest and most well-developed Unix, and I don't know why they call this Mako. I would think it would be ELF like Linux, but anyway, that's what it is, the Mako format. All right, so which key is embedded in the crypto accelerator? I don't remember. Oh, I can guess, though. I thought it was the device key. Nope, it's the UID key. Okay, I'm tired of being confused by this. Let's go back and look at the slides, because I can't keep it straight. So the
Slide 8.
Yeah, so let's go back here of all these layers of... There we are. So there's the device key, the passcode key, and the UID key. So the passcode key is the one that comes from your password. That one I understand. The UID is embedded in the accelerator. That's interesting. I would have thought that was the device key, but there's also something called the device key, which I have trouble understanding. The device key and the UID key seem redundant, but apparently not. Yep. Oh, the inputs are... Oh. Yep, you have to have your passcode, and there's a device key stored in the accelerator called the UID key, which is used to identify the user, I see, and the device key just identifies the device. Okay, so this is used with the passcode to make the passcode key. That does make some sense. Okay, anyway, like I say, lots of encryption, lots of pieces to a surprising extent. Apple is really not messing around. They really want to make this stuff secure. It's their whole thing, is that they are much more secure than things like Android, and they're right about that. Anyway, so it is the UID key in the secure enclave. All right, there's another one. Which feature mitigates heap corruption? Finally, back to something more general that I do know. Because this applies to a normal operating system like Linux, which I understand a lot better. iOS is really very complicated. Yeah, that's the automatic reference counting to avoid having too many frees or not enough frees to corrupt your heap. All right. All right. There you are. Good. No wonder you love him. And, all right. Good. So, stop this.